Imagine a place where the sun never fully sets on the high ridges, where the coldest shadows on the moon hide water ice that has remained frozen for billions of years. Imagine people living there, not for the 3 days of an Apollo visit, but for months at a time, working, maintaining systems, conducting science, building infrastructure. That is the ambition, not another set of footprints in a flag, a sustained human presence. We have already been there. Between July 1969 and December 1972, 12 men walked on the moon. The longest stay was just over 3 days. Then we left. For more than half a century, the moon waited in silence. Now the goal has changed. As of 2026, NASA has fundamentally restructured its approach. The Lunar Gateway, the planned orbiting station, has been paused. Resources that were once allocated to orbital infrastructure are being redirected to the lunar surface itself. The new focus is a moon base near the South Pole, developed in 3 deliberate phases. Phase 1, running through roughly 2029, is about establishing reliable access. NASA plans approximately 25 launches and 21 landings during this phase, delivering around 4 metric tons of payload to the surface. Early missions include Blue Origin's Mark 1 Endurance lander targeting the Shackleton Connecting Ridge and Astrobotic's Griffin lander. Astrobotic's Griffin, carrying more than 500 kilograms including a rover, and multiple additional CLPS landers carrying standardized science payloads. Instruments like the SCAL-PSS stereo camera suite for studying engine-plume interaction and laser retroreflector arrays for precise navigation. The first crewed landing is targeted for Artemis 4 in 2028. Later phases scale dramatically, aiming for roughly 60 tons of surface payload in Phase 2 and 150 tons in Phase 3, while introducing semi-permanent habitats, nuclear power, and eventually continuous crew presence. China is advancing on a parallel schedule. Chang'e 7 is planned for the second half of 2026, with a possible launch as early as August. The mission carries a hopping probe specifically designed to enter permanently shadowed craters near Shackleton to search for water ice and other volatiles. This is the opening move in the construction phase of the International Lunar Research Station, with a basic operational model targeted for the mid-2030s. 2 major efforts, 2 different international frameworks, both focused on the same high-value polar real estate. Why the South Pole? Certain peaks and ridges experience near-constant low-angle sunlight, providing a reliable source of solar power for much of the year. Only a short distance away, permanently shadowed regions that have not seen sunlight for billions of years are cold enough to trap water ice. Power and a critical resource in one geographic zone. That combination makes the region both the most practical location for a sustained base and the most strategically contested. This is no longer a question of whether humans can reach the moon. It is a question of whether we can remain there. And to answer that question, we must first confront the environment itself in far greater technical detail. The moon looks serene from Earth, a silent, silver sentinel that has inspired humanity for millennia. Yet, at a human scale, it is one of the most hostile environments we have ever attempted to inhabit. Modern exploration has pivoted toward the lunar South Pole, a region of massive geological interest and extreme environmental complexity. Here, the sun never rises more than a few degrees above the horizon. This unique geometry creates islands in the dark, peaks of eternal light where solar power is nearly continuous, surrounding permanently shadowed regions that have not seen direct sunlight for billions of years. Within these shadows lie reservoirs of water ice, a critical resource for sustainable habitation. But to reach them, we must survive a gauntlet of 4 environmental stressors: radiation, dust, thermal extremes, and partial gravity. We begin with radiation. Unlike Earth, the Moon possesses neither a thick atmosphere nor a global magnetic field to deflect the high-energy particles that saturate deep space. Galactic cosmic rays, consisting of high-energy protons and heavier nuclei, originating from distant supernovae, arrive at the lunar surface from every direction, 24 hours a day. Solar particle events, or SPEs, present a more acute threat. These bursts can deliver intense, life-threatening doses of radiation in a matter of hours, triggered by solar flares or mass ejections. In situ measurements from the Lunar Lander Neutrons and Dosimetry Instrument on China's Chang'e 4 recorded an average dose equivalent of approximately 1.37 millisieverts per day on the surface. This is nearly twice the typical daily value recorded inside the International Space Station. Without significant shielding, a year on the surface could result in doses exceeding 500 millisieverts. Regolith, the loose lunar soil, is our best defense. A few tens of grams per square centimeter will stop most solar particles, but cosmic rays are far more difficult to arrest. Meaningful reduction of galactic cosmic rays requires approximately 1 to 3 meters of compacted regolith. This mass acts as a physical barrier, absorbing the energy of incoming particles. However, at these depths, secondary neutrons produced by collisions within the regolith itself become a secondary radiation source. We must use hydrogen-rich materials to moderate these neutrons. Natural lava tubes, remnants of the Moon's volcanic past, offer excellent protection. However, these are rare, and their proximity to high-priority exploration sites is currently limited. The second major challenge is lunar dust. To the Apollo astronauts, regolith was more than just soil. It was a pervasive, mechanical adversary that threatened every system. Regolith is the product of billions of years of micrometeorite impacts. In the absence of wind or water erosion, these particles remain sharp, angular, and incredibly abrasive. A large fraction of these particles are smaller than 20 micrometers. Many fall into the respirable range, meaning they are small enough to be inhaled deep into human lung tissue. The interaction with solar ultraviolet radiation leaves these particles electrostatically charged. They don't just sit on surfaces, they cling tenaciously, defying standard cleaning methods. This dust acts like an industrial abrasive, grinding away at seals, bearings, and optical surfaces. It degrades the efficiency of solar arrays and fouls thermal radiators. When introduced into a pressurized habitat, regolith poses a direct ocular and respiratory hazard. Apollo crews reported lunar hay fever after tracking dust back into their lunar modules. Larger modern landers introduce the sandblasting effect. Rocket plumes can accelerate dust particles to hundreds of meters per second, damaging nearby infrastructure and sensors. Engineers are currently developing landing pads and protective berms. By using lasers or microwaves to sinter the regolith, we can create hardened surfaces to mitigate dust lofting. Thermal extremes present the third major hurdle. At the lunar equator, surface temperatures swing from a blistering plus 120 degrees Celsius to a frigid minus 170 degrees. Polar sites offer more moderate averages, but they introduce complex lighting geometry. Long periods of shadow within craters and short, intense sunlight on ridges complicate thermal management. Solar power is the baseline, but the 14-day lunar night and the energy-intensive needs of mining water ice drive the requirement for a more robust power architecture. NASA and the Department of Energy are collaborating on a fission surface power system. Targeting the 100 kilowatt class, these reactors are designed to operate autonomously for a decade. A reactor of this scale is essential for ISRU, the processing of local resources. Solar alone cannot sustain the high electrochemical loads required for deep space self-sufficiency. Finally, we address gravity. Lunar gravity is just 1/6 of Earth's. While we have decades of data on microgravity, the effects of partial gravity remain a scientific frontier. We know that weightlessness leads to significant bone mineral density loss and muscle atrophy. In microgravity, astronauts can lose up to 1.5% of bone mass per month. Partial gravity should mitigate these losses, but the threshold for protection is unknown. Many researchers believe that levels below 0.4 G may not be enough to maintain long-term health. Vision changes, fluid distribution, and immune function are all open questions. Long-duration stays measured in months or years will require new countermeasures and monitoring. These four environmental factors, radiation, dust, thermal extremes, and partial gravity, do not act in isolation. They interact continuously, challenging every piece of hardware and every human. Understanding these challenges is not just an academic exercise. It is the fundamental engineering requirement for becoming a multiplanetary species. The Moon is the proving ground.